tomorrow when we get together, I'm going to have this device for you. It's called a dissectable capacitor, and it consists, as do all capacitors, of two plates. These would be metal aluminum cups, one inside the other, that I can put opposite charges on, and an insulator in between, just like the Leyden jar that you probably made last year and got a shock from. That I will hook this up to a seat of EMF, a source of potential difference, and I will give a one charge to this inner cup and a different charge to the outer cup, and thus create a capacitor. And then I'm going to take the capacitor apart. Without touching it, I will pull the cup out, and then I will pull this plastic cup out as well, but here in this video I'm going to pull it out by pulling it down to here. Once I've gotten it apart, I will take my finger and I will touch this cup to neutralize it. And then I will take my finger and I will touch this cup to neutralize it. In fact, I will take this cup and I will touch it to that cup, so that, one had negative charge, the other had positive. I will touch them together. Then I will put it back together. Put the plastic down inside. I will put this inside of that. And then I will make an electrical connection between the outer cup and the inner cup. I will actually go over to this ball here, and you will get a spark. And you will say, "Whoa! Where did that come from?" And what we're supposed to learn from this is that the secret of a capacitor is not the charge on the two plates. It is the field between those two plates. That the energy of a capacitor is in the field between the plates. That is a key idea. Later on in the year, we're going to look at what's called an inductor. And you may recall from last year that when you send current through a coil of wire, you get a magnetic field. Well, just like a capacitor stores energy in an electric field, an inductor will store energy in a magnetic field. It is a key idea. Okay, the symbol for a capacitor is these symbols here that you have symbolically the two plates. What we don't see is that there's an insulator in between. If you were to put a conductor in between, like say ionized water, then when you put charge on one plate and opposite charge on the other plate, they would just a current would flow and they would discharge. So you need to have something that permits charge from moving from one to the other. And it turns out that you want them to be as close to one another as possible, because that increases the capacity to hold charge. It increases the capacitance. But if the field gets too strong, it will take this insulator and ionize it, and then it becomes a conductor, and that's called a breakdown. So that's going to be another topic we're going to look at, is this breakdown voltage of the capacitor. This is another symbol for a capacitor that we have not used before, but I think one of the reasons for this symbol is that this looks very similar to the symbol for an electric cell. The only difference would be with an electric cell you would have a short line for the low potential and a long line for the high potential. And they may have gone to this because people get confused. Did they mean that to be a short line, or was that just accidental that one is shorter than the other? So this makes it very clear. The other thing about this is that we are going to deal with electrolytic capacitors. And with an electrolytic capacitor, that insulator in between is created the first time you hook it up. There is a material in here which oxidizes, and that very, very thin layer of oxide is what your insulator is. And that's a very effective way to make a capacitor, But the problem is if you then hook up that capacitor backwards, then instead of creating that oxide, you would destroy the oxide, which would release oxygen gas, and the capacitor could explode. Please don't do that. And it's not a very impressive explosion, but you would destroy the capacitor. With electrolytic capacitors, we need to be as careful as we can to hook them up with correct polarity. And that's what this different symbol here is about. Okay, I state as a fact, without justification, that for capacitors, the charge that you put on the plate, and you would put the same magnitude charge on both plates, but opposite sign, is proportional to the potential difference between the plates. This is experimentally determined. Take it as an empirical fact. If we change proportionality to an equation, it looks like this, and that constant of proportionality is what we call capacitance. So there then is the definition of capacitance. If you like, it is the charge on the capacitor divided by the potential difference, the charge per potential difference. But I prefer to write it in this form because I have a mnemonic that says AQ CV, where it's this guy from Jersey who's with the mob, and he says, "Hey, Use, go see the boss, whose name is Vito. AQ CV." And you don't want to go see V, because he's a mean guy. That's how I remember this. Q, CV. All right, you're going to have to suffer through that, because I have to keep reminding myself who goes where. Very important that capacitance is determined by the geometry. The area of these plates, how far apart they are, and it turns out also on what material you put in between, but that will come much later. It does not. Capacitance is a constant. It does not depend upon Q. It does not depend upon V. The units of capacitance are farads, which would be equal to a coulomb per volt. Remember that a coulomb is a crazy large amount for static charge, and so is a farad, a crazy large amount of capacitance. We will typically deal with picofarads or femtofarads, or at the most microfarads. That farad is big, just like capacitor is big. Okay, now I'm going to lead you through deriving these formulas, and I will do the first one, and then I want you to mimic that to do these two here. And to the extent that you are unable to mimic me, you will listen to me doing it. But try not to just listen to me doing it. You will benefit nothing. You must stretch yourself. You must try to do it yourself. So the first thing you do with this is you focus on the field. That's, after all, where the energy is of a capacitor. And I want to capture what is that field like there. And so I'm going to use Gauss to determine that field. That what I will do, here you go. Sorry. I'm going to use Gauss to get that field in terms of the charge that is on the capacitor. And then I'm going to, once I get E as a function of Q, I will put that into this equation, and that will get V as a function of Q, and then I will come to this expression, A, Q, CV, and I will put in V as a function of Q. The Q's will fall out as they ought, and I will get capacitance purely as a function of the geometry of the capacitor. And one other additional point, capacitance is always positive. So if you get an answer that's negative, then fix it. Okay, so first I have to use Gauss to get E as a function of Q, and that's a matter of choosing a Gaussian surface. And I'm going to choose a Gaussian surface which is a cylinder, but I want to completely enclose all of the charge that is here on this inner surface. So I'm going to ignore the fact that there's fringing here at the edge and pretend like there's not, that it's uniform throughout. This field in here is uniform. I put a Gaussian surface that captures that. And then I need to write Gauss's law, and I need to talk about E in order to evaluate this function. So there's Gauss's law, and then I point out that E is parallel to the area across here. It's perpendicular to the area here, and it's equal to 0 across there. So you go over the whole Gaussian surface and talk about E relative to A. It's also constant across that surface there. That permits me to evaluate this integral. And I get that Q, the charge on the capacitor, is equal to epsilon. The E is constant, so I can pull it out, and the only part where I got a non-zero when I did E dot dA was across the top, so I get A just once. So there is E as a function of Q. Then I will write this expression, and I will put in for E this expression here. But first let me stop and point out that I haven't written this correctly. There should be a minus out front and there should be a dot there. But what I want you to do is always evaluate the integral from the low potential to the high potential. If you evaluate the integral from the low to the high, then you are going opposite the direction of the field. The field would point away from the high potential and towards the low. So your ds, the path that you're taking, is anti-parallel to E. So when you do E dot ds, you're going to get a negative out of that, and that negative together with this negative out front makes it go away. So this expression works, but only if you evaluate it from the low to the high potential. Please be very, very careful to do it that way. Okay, and then I put in the expression for E, evaluate the integral, and I end up with this. V is a function of Q. I put that into this expression here, and you end up with the Q's go away. D is going to be in the denominator. This denominator with the epsilon A is going to end up on top, and there you have it. There is the capacitance, and it is purely due to the geometry of the capacitor. Please notice that the dimensions here, that's our meters squared, this is meters, so the dimensions of C are the permittivity constant times meters, and that will be true for every single one that you do. Please be, that will help you to check your work that you get. Permittivity constant times meters as the dimensions, that's good. Notice that the dimensions of capacitance are going to be coulombs per joule, coulombs per volt, and a volt is a joule per coulomb, so the dimensions of farads are coulomb squared per joule. That doesn't seem like permittivity times meters, but the dimensions of the permittivity constant are such that it does work out. Always. Permittivity constant times meters. And here is stuff that I said, but we'll put it out here explicitly about how you need to always integrate from the low to the high potential, and what happens as a result of that, and so you get this expression here. Alright, now I want you to do what I just did for this, and it would start by thinking about what is the field like, what Gaussian surface would capture the symmetry of that field, use Gauss to get E as a function of Q, and then put that into the expression V equals the integral E times ds. Evaluate that from the low to the high potential, and that's okay. And then finally put that into the definition of capacitance. Okay, you try to do it. If you are frustrated, start the show again and watch what I'm doing until you say, oh, okay, and then try to do it yourself again. Stop the show. Then start it again every time you get frustrated, or when you are done, just to check what results you got. Okay, so here we go. You have started the show again because you got frustrated. You first want to choose a Gaussian surface that captures the symmetry you've got. So I'm going to do a cylinder. Notice I want the sides of the cylinder to be between these two because I want to find the field between these two. That is the key thing. What is that field as a function of the charge? Also, notice that I want it to enclose all of the charge. So again, I play fast with the truth and I pretend like there's no fringing at the end, so I'm enclosing all of the charge. So here is a description of the Gaussian surface. You need to give me an explicit statement of what was that Gaussian surface you just drew. Do a good job of it. This is exactly what I want it to look like. This is a cylinder of height L, and my Gaussian surface is going to also be that full L. Then you put that into Gauss's law, and talk about E being parallel to dA and constant at the sides and perpendicular at the ends, and so I end up with the E as a function of Q looking like this. I would need to move those over there with the Q. Then I put those into this expression for V as a function of E, and I put in that expression for E that I got from this in here, evaluate from the low to the high, and when you evaluate, notice that what we've got here is R in the denominator, dr, so that is going to be the natural logarithm of R. We evaluate that from B to A, from the low potential to the high potential, and you end up with putting A in to this expression. Notice you got that negative there. Negative natural logarithm of A minus negative the natural logarithm of B, which is like the natural logarithm of B minus the natural logarithm of A, and you recall that the difference of natural logarithms is like a quotient. So there is the expression for V as a function of Q, and then we put that into the definition of capacitance, and the Q's go away, and this was going in the denominator, so this part here hops up to the top, and this was in the numerator, so that's down in the bottom. Please notice the dimensions that you got here. The top would be permittivity constant times meters, and the bottom is dimensionless. So it's exactly right. Please note also, if B was smaller than A, then, or if you had the natural logarithm of A over B here, with the smaller on the top, then what you get when you take the natural logarithm of something smaller than 1 is negative, and the capacitance can never be negative. So check that out. Make sure this is giving you the right result. If it's not, go back and fix it. Again, I want you to try to find the capacitance of a spherical capacitor, and if you find yourself frustrated, then turn the show back on and watch what I'm doing, and stop as soon as you can and try to do as much as you can yourself. Watching me do it will be very easy, but you will gain nothing from it. You must be able to do this. So the first step would be to think about what is the symmetry of the field in here, what Gaussian surface will capture that, and I think what I want is a spherical shell lying between the two, because I want to know the field between the two. So here's my Gaussian surface. That's the language you ought to use, folks. All of this. Learn to do it. And then I'm going to use Gauss. There's Gauss. And I'm going to talk about E as in relationship to dA. And it's everywhere parallel and everywhere constant. And so out of this comes epsilon E, and then the area of that shell, which is 4 pi r squared. And so E as a function of Q looks like that. And then I'm going to do it into this expression where I want to be very careful to go from the low to the high potential, and then I don't need the dot product and I don't need the negative. And what I'm going to do is to that's very interesting. I'm going to put this value in for E, and I don't, if I were to evaluate it from A to B, then that would be the negative of evaluating it from from B to A. So that's where that negative comes from. I'm a little disappointed with my work here, but ultimately, if you do that, here is, I forget that negative. There is, but look, what you get out of this. That's r to the negative 2. So when you do the integral, you end up with r to the negative 1 and a minus out front. Haha. So I was covering for myself. But I've got to do it. Oh my. I've got to do it. Here we've switched back to B to A. Oh, shame on me. From B to A. So you first put in the A, and then you put in the B, and the common denominator would be AB, and this would have a B on the top. That would have an A on the top. Okay, and then you take that expression for V as a function of Q, and you divide it into Q, so the Q's go, and you end up with this up on top, and this up on top, and that in the denominator. Now, something went goofy here. I can't justify this, but if the answer had been A minus B here, and A was the inner radius and B was the outer radius, then I would end up with a negative in the denominator. Capacitance can never be negative. So I want to make sure that this is the result, even if I don't understand what I did in here. I'm sure if I had struggled with it I would, but I'm trying to go fast here. Make sure your answer is positive. And it should come out naturally from doing this correctly. I'm embarrassed. Okay, the last one you did was the isolated capacitor. And all you do is take the result for a spherical capacitor and you let this outer ring go to infinity. And so what you have is this result here, but if B is much larger than A, then what I want to do is divide the top and the bottom by B. And it's AB divided by B, and it's B divided by B minus A divided by B. But if B is much, that's just becomes an A. This becomes a 1, and that goes to 0 if B is much larger than A. And so you do get this expression, and that's how you should do that. Thank you very much.